Let's talk about the binary tree traversal techniques. If you're preparing for a coding interview and practicing lead code challenges, you should know the difference between these three techniques. And this video will help you to understand it. Tree traversal techniques include various ways to visit all the nodes of the tree. It refers to the process of visiting or accessing each node of the tree exactly once in a certain order. Depending on which order you choose, you will have different results. For example, in the Inorder traversal, first you iterate through the left subtree, then the root, and then the right subtree. In the Preorder traversal, you take the root, then you go to the left subtree, and then the right subtree. In the Postorder traversal, first you iterate through the left subtree, then you go to the right subtree, and only then you append the root. So how to remember that easily? Remember that the right subtree comes always after the left subtree, and the root is placed at the place depending on which prefix you have before the order. For example, in the in order, you have the in prefix, so you have the root inside. In the preorder traversal, you have the prefix pre, which means in the beginning. That's why you have the root in the beginning. And in the post order, the post prefix indicates the end. Therefore, you append the root to the end. Regardless of which technique you choose, all these three options belong to depth first search or DFS algorithm. DFS is a recursive algorithm, meaning it calls itself to traverse the graph. So here's a step-by-step explanation of the DFS algorithm. First, you have to initialize. Choose a starting node and mark it as visited. Then you have to explore the neighbors, visit all the nodes adjacent to the current node that have not been visited before. Then you want to mark as visited, and the next step is backtrack. Once all unvisited neighbors of the current node have been explored, backtrack to the previous node. And the last step is to repeat. Continue exploring neighbors and backtracking until the entire graph has been traversed or a dead end is reached. So let's move to the use cases of each technique. You can use the in-order traversal in displaying items in a sorted order. Imagine an online bookstore with books stored in a binary search tree where each node is a book, ordered by title or price. All books are displayed to users in alphabetical order, which is useful for browsing or catalog organization. Another use case is data validation in trees. In medical or financial applications, BSTs might store patient records or transaction amounts in an ordered fashion. By performing an in-order traversal and checking if each successive element is greater than the previous one, you can confirm the data integrity. You can use the pre-order traversal in such applications as file system organization or building or copying trees. Think of a file system where each directory or folder contains subdirectories and files. This structure can be represented as a tree. You get an organized display where each main directory appears before its nested folders and files, which is ideal for a hierarchical directory listing. Building or copying trees. Suppose you are creating a copy of a network configuration tree that includes various routers and switches in a hierarchical setup. You recreate the original structure by visiting each node in the exact order needed for an accurate duplicate. So where would you use the post-order traversal? The use cases for post-order traversal are deleting or freeing resources and project task dependency management. In a cloud computing environment, imagine a tree where each node represents a virtual machine instance that depends on other virtual machines. Post-order traversal ensures that all dependencies, children nodes, are deleted before deleting the root node, preventing FAANG dependencies. What about the project task dependency management? Imagine you're managing a software development project with a dependency tree where each node represents a task, and some tasks depend on others. For example, build backend depends on setup database, which in turn depends on defined data models. Post-order traversal ensures that for each task, all dependent tasks are completed before the main task itself. This is crucial for projects where you can't move forward on a task until all prerequisite tasks are done. Now let's move to the code. As I said, all these techniques are DFS algorithms, which means they are stack-based. That's why we have a stack variable in all three cases. Let's explore the in-order traversal first. Set the current variable to root, and then the first while current loop continues moving left, appending nodes to stack until it reaches end of the left subtree. In the first steps, you will append 1 to the stack, then you will append 2 to the stack, and then you will append 4 to the stack. There is no node on the left. Pop the last node from the stack and move it to the result. As you can see here in the result, the first node is 4. Go check if there are nodes on the right side. It's empty. Pop the last node from the stack again and move it to the result. Go check if there are nodes on the right side. There is 5, append it to the stack, and in your current stack you have 1 and 5. There is nothing on the left side, that's why you are taking the last node from the stack and move it to the result. Now your stack contains only 1. Go check if there are nodes on the right side. It's empty. Pop the last node from the stack again and move it to the result. Now you don't have any nodes in the stack. So go check if there are nodes on the right side. There is 3, append it to the stack. There is nothing on the left side, that's why you are taking the last node from the stack and move it to the result. Go check if there are nodes on the right side. There is 6, append it to the stack, and your stack will contain 6 right now. There is nothing on the left side, that's why you are taking the last node from the stack and move it to the result. And now there is nothing on the right side, that's why you finish the iteration. So what about the pre-order traversal? It's very similar. You also want to set the current variable to the root. And in the while current loop, we immediately append current value to the result after appending it to the stack. This means we are recording each node as we reach it. So after the first iteration, you will have 1 in the stack and 1 in the result. Then you will have 2 in the stack and 2 in the result. Then you will have 4 in the stack and 4 in the result. So what do you do next? After reaching a non-value, the end of the left subtree, we pop a node from a stack, set current to the right child of this node, and repeat. So your stack will contain only 1 and 2. There is nothing on the right side, so your stack will include only 1. You are currently at the node 2. On the right side you have 5, so append 5 to the stack and to the result and go left. There is nothing on the left side. Pop 5 from the stack and your stack will contain only 1. There is nothing on the right side as well, so pop 1 from the stack and go right. Append 3 to the stack and to the result. There is nothing on the left side, so pop 3 from the stack and go right. Append 6 to the stack and to the result. There is nothing on the left side, pop 6 from the stack and go right. There is nothing on the right side as well, therefore you finish the while loop. The post-order traversal differs a bit from the in-order and pre-order traversal. Here you set the stack to the root. The while loop iterates as long as there are nodes in the stack. So first you have 1 in the stack. And in each iteration, the last node in the stack is removed and appended to the result. If node left exists, it is pushed onto the stack. If node right exists, it is also pushed onto the stack. So you pop the 1 and you append 2 from the left side and 3 from the right side. Now you pop 3 and add to the result. You have only 2 in the stack. We are at the node 3 right now, and there is nothing on the left side. There is 6 on the right side, so you append 6 to the stack. And you pop 6 and append to the result. We are at the node 6 right now. There is nothing on the left side. There is nothing on the right side. So pop 2 from the stack and append to the result. We are at the node 2 right now. Append 4 and 5 to the stack. Pop the last node, which is 5, and append it to the result. There is nothing on the left side. There is nothing on the right side. So you pop 4 from the stack and append it to the result. Now your stack is empty. We are at the node 4 right now. There are no nodes anymore, so you finish the iteration. That's it. Thank you for your attention and I hope you liked it. If you did, click the thumbs up button and follow for more. See you in the next video.